For a given function field f, an adele in this function field is defined as a mapping from the set of places to the function field, and for each p, we will assign a function alpha p such that alpha p lies in OP for almost all places. So indeed, we can regard, or we can view an adele as a kind of sequence where the places determined by the places of the function field. So the p components determined by the places of the function field, and at each component we will assign a function alpha p, such that these functions lies in the corresponding valuation ring for almost all places, or equivalently, these functions does not lie in OP for finite many places P in PF, because we have infinite many places, and if alpha P lies in OP for almost all places, so that means there exists finite many locations, P components, such that this assigned function, the function at the P position, is not going to be an element in the corresponding valuation ring, only for finite many places. And in this kind of sequence can be seen as element of the direct product of the function field, which is taken over the P when P runs through all places. And we will denote such a structure shortly by alpha P. And for the computational reason, indeed, we consider another equivalent statement. So that means alpha P is not in OP, means that by the corresponding discrete valuation maps and the discrete valuation rings, indeed, equivalently, we can state this statement as alpha P of VP of alpha P is negative for finite many places P in F. So in general, whenever we want to see that, whenever we want to prove or whenever we want to show a structure, in general, we work with discrete valuation maps. For instance, if you consider the whole set of adeles of a function field, like consider all possible sequences that satisfies this property for finite many places, is formed a vector space over the constant field K, and it is called the adele space of F. And in order to see that this set has a vector space structure, first is a vector space over K. First, we see that for a non-zero constant C and an alpha, adele alpha, so that means this kind of sequence whose components are the functions alpha P, such that VP of alpha P is negative, such that VP of alpha P is negative for finite many places P. And what we want to see is that in the first axiom, we want to see that C times alpha, if we consider the multiplication by a scalar as a component wise, so that means each function at the pth component is going to be multiplied by the constant C. Indeed, we can see that this is also adele, because if we check the valuations of this each component, by the properties of the discrete valuation map, this is going to be exactly Vp of alpha P. And we know that this is 0 for finite many P. So that means this adele is also satisfies this property for finite many places in P. And in order to see that the sum of the two adele is also adele, let me consider, or let me denote two adeles by alpha and beta, or more explicitly, alpha contains the functions alpha P at its coordinates such that Vp of alpha P is negative for finite many places. And let me denote this finite many places by Pi1 up to Pis. And let me write adele beta more explicitly with its components beta P, such that they have negative valuations for finite many places P. And let me denote these places by Pj1 and Pjr. So these places are not supposed to be distinct necessarily. But at least we know that for finite many places, we have this property. And now our claim is that when we consider the component-wise addition, we want to see that their components, the valuations of their components is going to be negative, strictly negative for finite many places Pf. And indeed, our final claim is going to be in that these finite many places is determined by this Pi and Pj's. But in order to see that more explicitly, let me give an observation. If you consider a function field and two functions x and y inside of it, and for the simplicity, for the moment, I'm going to only consider the simplest case. So I suppose that they have poles only at the places P and Q, respectively. So that means P is a pole, P is the unique pole of X and Q is the unique pole of Y. Then my claim is that X plus Y can only have poles at P or Q. Or in general case, indeed, we can extend this statement like the sum of the two functions can have only poles at the poles of the each components. So at the poles of X and the poles of Y. So, but let me show how this statement works, and you can generalize it. In this simplest case, if we suppose that if sum of these two functions has a pole at a distinct place R, which are different from the poles of X and Y, that means its valuation at this place is going to be strictly negative. On the other hand, by triangle inequality, we know that this valuation is bigger than or equal to minimum of the valuation of each function at R, but P is the only pole of X, so that means this valuation is going to be bigger than or equal to 0, and similarly, Q is the only pole of Y, so that means valuation of function R at valuation of the function R at the place, any distinct place different from Q, is going to be positive. But this gives us contradiction. So this is why when we consider the sum of the two functions, if we have an idea about the poles of each component, we can conclude the poles of this summation. And as a generalization of this observation, now we can see that the poles of this summation is determined by the poles of each component. So this valuation can be negative for finite many places. And indeed, this finite many places is determined by the finite union of this finite many places, PIs and PJs. And this shows us indeed A of A, which contains all adeles of a function field, forms a vector space over the constant field K. As an example, and in the meanwhile, this is also definition of what is called principal adele. Later we will understand that this is also notion of the generalization of the principal divisor for a function of a function into the setting of the adele space. And this is going to be adele, so that means we can view them as mappings, but at each P component, we are going to assign the same function X. So in other words, this is going to be a kind of sequence whose components are formed by only one function, X. So this is also adele. So in order to see that, we need to see this is an adele, because we need to understand that for how many places this valuation is going to be negative. But by corollary 1.3.4, we know that every function in the function field has only finitely many poles. So that means VP of X is negative for finite many places in P. And this shows us that such a structure is also adele. And thanks to this principal adele, thanks to this example, we can embed our function field into the adele space by assigning each function by the principal adeles. And this also allows us to remove the valuations of the function fields to the adel space. So that means we can also define the valuation of an adel by looking the valuation of the function which is located at its pth component.